today we start off by using those percentages to tell us how much stuff we have. Okay. Okay, so, and this is not new math either, okay? If you got 80% on a test, and the test was worth 50 points, what did you score on the test? Well, you'd take 80% of 50, right? Which you usually do by moving the decimal place over twice. 80, move it over to 0.8, times 50. You get 40. If you got 40 out of 50, that would have been 80%. Right? Well, that's what they use these percentages for. When you dig ore out of the ground, it's not all the metal you want. It's already reacted with something. Okay? So you're going to find it as part of an ionic compound. But you want to know how much iron there is in that iron ore. So to figure out how much iron there would be, you would multiply the percent by the total mass to find the mass of that element. Okay. So here's how it works. Okay. How much aluminum is there in 450 grams of aluminum carbonate? Well, I'm going to do what it says up here. I'm going to take that, multiply that percent. So that means I'm going to need to know the percent that's aluminum. Okay. And so that would be the grams of aluminum over the total grams. Times 100%. Okay, so that means I have to add up aluminum carbonate. So that's 2 aluminums. So that's 2 times 22.99 is 55.9698. 2.99. No, 45.98. Sorry, 45. 45.98 grams of aluminum. Okay, so I got to distribute that 3, so there are 3 carbons, and that's 36.03 grams. And I've got 9 oxygens. And 9 times 16 is 144. That's 1, 0, 10, 16, 7, 8, 226.01 grams. Okay, so I've got a total of 226.01 grams, and my aluminum weighed 45.98 grams out of that. So this is just like the homework, what we learned on Friday. Find that percent. So 45.98 divided by 226.01 times 100% is 20.34%. There were 4 numbers in there that in my math, so I kept 4 numbers. So that's the percent that's aluminum. So I have a total of 450 grams. 20.34% of it is aluminum. So the grams of aluminum is going to equal 450 grams, the total grams, times 20.34%, which is 20.34% means over 100, so move it back twice, times 0.2034. Percent means divide by 100, that means move the decimal place back twice. So 450 times 0.2034, and I get that there's 91.5 grams of aluminum. So that means when they dig the rock out of the ground, most of what they get is not aluminum. Most of it's waste. Okay? And actually aluminum's like this, and it always comes as part of a compound, which is why, and to get the aluminum away from that compound, they use electricity. And that's why it's important to recycle aluminum, because it takes a lot more energy to tear the aluminum away from the other stuff than it does to melt the aluminum can you already have. Does that make sense? So it's about energy savings. It's not about saving the aluminum, it's about saving the electricity to make the aluminum, which is saving the carbon dioxide going into the atmosphere. So the iron ore they dig up. When you dig up iron ore, you never find iron in the ground unless it's a meteorite that's hit the ground. Okay? But the iron ore they dig up is iron 3 oxide. If you dig up 155 grams of iron 3 oxide, how many grams of iron will you have? So to figure out how much iron there is in 155 grams of iron 3 oxide, I can figure out the percent that's iron. That would be the grams of iron over the total grams times 100%. So I need to assume I have 1 mole, so I can say I have 2 moles of Fe and 3 moles of O. 2 Fe's times 55.85 is 111.70 grams. 3 oxygens times 16.00 grams is 48.00 grams, so that's 159.70 grams. So the grams of iron was 111.70 grams. The total grams 159.70. So 111.7 divided by 159.7 times 100 gets me 69.94% iron. So this is a lot bigger payoff for your buck. Instead of getting 20% of the metal, you get almost 70% metal. And so the grams of iron is going to equal that 155 grams times 0.6994. Move the decimal place over twice. What is the percent? 155 times 0.6994 equals that I'll have 108 grams of iron. And you can check really easy. It says 108 grams, divide by 155. Times 100. Comes pretty close as a rounding error. Okay. That makes sense? Really hard? So that's what they use it for. Fact is, that's what I used it for. I worked in a quarry, in a lab, and we guaranteed that our rock was 96% pure. So I would walk down the line, and there were samplers along the line that would give me a sample of rock that I would grind up and test to see the percent. And the rock I was digging up was calcium sulfate. Okay? It was calcium sulfate. And I would check for the percent sulfur, because that was the only place sulfur should show up anywhere in the area. And by how close the percent sulfur matched the percent that it was supposed to be, that told me how pure our rock was. I mean, that's the test they do. They check to see what percent it is. Okay? So that's how it gets used. Okay. Now, you can go backwards. We went from the formula to the percentage. You can go from the percentage back to the formula. Don't know if you've noticed this about the math you've done, but they always teach you to do it backwards right after they teach you to do it forward. Because math goes back, if you solve it one way, you can always solve it the other. Until you get to quantum mechanics, that works. Okay? So, it works here. And what you get is something called the empirical formula. The empirical formula, empirical means from lab data. That's what it means. So they measured it. What formula do you get when you measure the lab data? So the lab data they're talking about is tearing it apart into its elements, those percent numbers we just talked. They find the percent of every element. And from that empirical data, that stuff from the lab, they can figure out what the formula was. Okay? Now, compare that to the molecular formula is what the real molecule looks like. Empirical formula is the lowest ratio. The real formula is the molecular formula. Now, for ionic compounds, we always do the lowest ratio. That when it says Mg2 plus and O2 minus, we don't label it Mg2O2, it's MgO. Because it already adds up to 0. Ionic compounds are always the lowest ratio, already. Molecular compounds might be the lowest ratio, they might not. The two can be the same. But they don't have to be. So CH2. I can say for certain that CH2 is an empirical formula. So, how do I know it's an empirical ratio? Because I can't get lower than 1 to 2. Is it a molecular formula? Do you know of a molecule that's CH2? Are you sure it's not a molecular formula? Are you sure there's nothing that there is no molecule CH2? So if you don't know for sure, you can't say whether this is a molecular formula or not. But you're certain that it's an empirical formula. C2H4, I am certain, is a molecular formula because it's not the lowest ratio. The lowest ratio would be CH2. Okay. C3H6. I'm certain it's an empirical, it's a molecular formula. Now, I happen to know that both of these exist. Okay? Because C2H4 is ethylene, and if you put a lot of those together, you get polyethylene. Okay? Plastic. But these both exist, and they both have the same empirical formula. Multiple compounds can have the same empirical formula. So when I tear it apart to percentages, I'm not going to be able to tell the difference between C2H4 and C3H6. But I will see that there's 2 hydrogens for every carbon in this compound. So I'll be able to get the lowest ratio, but I won't get I may not get the actual one. Because the percent carbon is going to be the same in all 3 of these. Everybody see why the percent carbon would be the same? It's got 3 times as much of everything, and you're dividing by 3 times as much. 3 times as much carbon divided by 3 times as heavy, you're going to end up right where you belong. So all these would have the same percent carbon and percent hydrogen, but they'd be different molecules. Well, 2 of them be different molecules. CH2 doesn't really exist. H2O. Is H2O an empirical formula? Yeah, it's the lowest ratio. Is H2O a molecular formula? Is there really molecules of H2O? Yes. So it's both. How did you know it was both? Because I knew about water. Otherwise, you can't be sure. And I'm not going to expect you to be sure, unless it's something you know really exists, like carbon dioxide. I'm not going to surprise you. Okay, so to find it, just find the lowest whole number ratio. If they give you a formula, just simplify the ratio. It's like simplifying fractions. Just like your math teacher wouldn't let you turn in a problem that said 4/8 as your answer. Well, they would, but they'd mark it wrong. They'd let you turn it in. They just wouldn't give you credit for it. Take off partial credit because you didn't reduce. Right? Same thing here. It's the same process. If there's more than one compound, if there's more than one element, though, all of them have to be divisible by the same factor. So for C6H12O6, okay, look at the subscripts. Do they have a common factor? Could you, just like you were simplifying fractions, right? They have a common factor. The common factor is 6, right? So I divide all the subscripts by 6. So instead of 6 carbons, I got C. Instead of 12 hydrogens, it's 2. And instead of 6 oxygens, it's 1. So the lowest ratio is CH2O. Okay. Now, actually, there's a lot of chemicals that have this empirical formula. Okay. And it looks like they took carbon and added water to it. Like they hydrated carbon. So all the chemicals that have this empirical formula are called carbohydrates. That's why they're called carbohydrates, is because their empirical formula is CH2O.
It's like carbonated water?
Carbonated water, no, we're talking about carbohydrates like salts, or like sugars and starches. Pasta has lots of starch, which is a carbohydrate. Okay? The places we get our energy. Okay? They give us energy without any other nutrients. Oh. Okay. Okay, so lots of things can have the same empirical formula. Hey, what is the empirical formula for CH4N2? Yeah, I say, well, I can divide these 2 by 2, but I can't divide the C. Unless I can divide all 3 of them, this is the lowest ratio. got to be the same number all the way through. Okay. Okay. Now remember, this is not just a ratio of atoms. It's a ratio of moles of atoms. That in CH2O, for every molecule, in every carbon, for every carbon atom, there'd be 2 hydrogens and 1 oxygen. But in a mole of this, there'd be a mole of C, 2 moles of H, 1 mole of O. Right? Isn't that how we? That's why we could add them up. And that's going to be our secret tomorrow when we turn these back into formulas. Okay. So, which of these could be an empirical formula? I like this style of question. Because it could, you can't just guess. If you don't know, you're just guessing. You can't eliminate anything. Darn, more than one. What do you mean more than one? Okay, well, is N2O4? Can you simplify it? Yeah, divide by 2s, right? How about N2H6? By 2. How about N2O5? Nope, so that one's an empirical formula, so that, okay. Okay. If an empirical formula is CH2, what's a possible molecular formula? Okay, people automatically look through and say, "Oh, C4H8." That's twice as many H's as C's, right? What about A? Is A a possible molecular formula? Yeah, it's the lowest ratio, but it could also be the right one. Are you sure it's not a molecular formula? Said, okay, it could be either one of those. You're not sure about CH2. Does that make sense? Okay. There is no element X, Y, or Z. Oh, there's a Y, yttrium, sorry. So, survey says it's easy as 1, 2, 3. Right? It's easy as 1, 2, 3. Because all of those were divisible by 3. Leaves you with 1, 2, 3. Okay. So what's going to be different about X, Y2, Z3 versus X3, Y6, Z9? Well, the molecule has 3 times as much of everything, right? So it's going to be 3 times as heavy. So that's going to be the difference that we're going to be able to measure, is how many times heavier it is. So to turn an empirical formula into a molecular formula, well, since the empirical formula is the lowest ratio, the actual molecules got to weigh more, or the same. It can't weigh less. It's got to weigh the same amount if they're the same, and if they're not the same, it's got to weigh more. The molecule has to weigh more. But it won't weigh 1 gram more. It won't weigh some 1.97 grams more. It'll weigh a whole number, multiple times more. It will weigh twice as much, or 3 times as much, or 6 times as much. But it's got to be a whole number. You've got to be twice as heavy or 3 times as heavy, because you got to have twice as much of everything or 3 times as much of everything. So that's why we need the density of the gas, because we took that density and turned it into molar mass. Because that's what's going to be the difference, is the molar mass. So a thing we can measure is the actual molar mass. if it's a gas at STP. We have other ways of doing it if it's not a gas at STP, but for right now, for us, that's how we calculate it, if it's a gas at STP. So if you take the actual molar mass, how heavy the real molecule is, divide it by how heavy the empirical formula would be, you will get a whole number. That will tell you how many times heavier it is. Why is it that many times heavier? Because you got that many times of everything. You're going to get a whole number, so you multiply the empirical formula subscripts by that. So you can change those subscripts. So this is just going backwards. You saw C6H12O6 was CH2O. Now, with a molar mass, we're going to be able to go from CH2O back to C6H12O6. Whoa. It's gone in some bizarre places. Okay. So, for example, this one gives me a headache. Ibuprofen has an empirical formula of C6H8O and has a molar mass of about 192 grams per mole. What is its molecular formula? Well, I know 6 C's, 8 H's, and 1 O. So ibuprofen, there's its empirical formula, and they weighed its molar mass. Probably didn't do this one with the density of a gas, since ibuprofen's not a gas. Carbon is 12.01 grams off the periodic table. Hydrogen's 1.01 grams, and oxygen 16.00 grams. So that's 72.06 grams of carbon, 8.08 grams of hydrogen, and 16.00 grams of oxygen. That adds up to 0.14, 14 and 2, 16, 2 and 7 is 9, 92.14 grams. Well, if I take that 192 grams, that's what the real 1 mole is, and I divide it by, that's a 6. It's 96.14. 2 and 8 is 10, and 6 more is 16. Yeah, I did 14 for some reason. Okay, and I take that 192 grams and I divide it by 96.14 grams. You push those buttons on your calculator, you will get a number really close. 2.00. Actually, the grams cancel out, so you don't have any units. You got a whole number, 2. So that means ibuprofen is twice as heavy as C6H8O. So it's C12H16O2. Make sense? It's twice as heavy, so it's got twice as much of everything. You'll get the same percentages. If you tore those apart, you always get those same percentages. You couldn't tell the difference between those two based on percent. You have to take on molar mass. This one has to come out to be a whole number every time. Yeah. So and it's going to. This one came out 1.997. So if you round it all, you're going to hit 2. Okay. Compound has, that's a ClCH2. It's not CiCH2. That doesn't work. 2 H's, 35.45 grams, 12.01 grams, 2.02 grams, 7, 8, oops, I had an 8, sorry, forgot the 1 there. 8, 4, 2, 4, 9, 49.48 grams. 47, 2, 4, 9. Yeah, I got it right this time. So 98.96 grams is what the real thing weighs. The lowest ratio weighs 49.48 grams. The answer comes out to be 2 again. Doesn't always end up 2. This time it did again, twice in a row. What if they were the same? Then the 2 are the same, right? But these are not the same. I have twice as much, so I don't have a Cl, I have 2 Cls. I don't have a C, I have 2 Cs. And I don't have an H, I have 4 H's. Pretty easy to do. But that's where I want to stop for the day. So, here is a start to your homework.